right. Are there any questions on anything? All right, so last time, this problem we're looking at, you can kind of interpret just geometrically. It doesn't even have to be a graph theory question. So you just place endpoints on a circle, and then you draw a chord or line between any two. And for the simplicity of the problem, otherwise I don't think the answer is going to be simple, is that you assume that for any two of the lines, they intersect at one point, but you don't have three of them intersecting at one point. If you had 3 points on the circle, but this isn't the best example. But what I'm saying is that you won't have something like this, where three of them intersect at one point. So with these conditions, there's kind of two natural questions to ask: is how many points of intersection do we see in the graph, or I guess inside the circle, which we're probably going to interpret as a graph later, and then how many regions are you dividing the entire circle into? So just geometrically looking at how this is done, the points of intersection is a pretty straightforward question, as long as you just visually see what's happening. So again, usually we just say chord because of course everything that's lying out here for the line is irrelevant. We're just looking at what happens inside. And so it should be pretty clear here visually that you're going to need 4 points in order to create an intersecting point from those lines or chords formed by the 4 points. And the important thing here is for simplicity, we're assuming no 3 intersecting at 1 point. So therefore, exactly every single 4 points on the circle, any 4 that I pick, will uniquely determine a point of intersection inside the circle. And clearly there is no ordering, right? Once you just tell me there's 4 points, when I draw these 6 lines, it's going to create 1 point of intersection inside. So therefore, out of the n points, if I choose any 4, I'm getting a point of intersection. So there's n choose 4 number of points of intersection. So the harder part to look at is looking at the number of regions. So I briefly mentioned this last time, is that whenever you're drawing these lines, right, whenever you have an intersection, we're going to create a vertex doing that. So therefore, if I look at the circular region inside, I can now convert this into a planar graph. So if I apply Euler's identity somehow here to count the number of faces, which is the number of regions, at the end, I will have to subtract out 1 on the portion outside. So I guess there should have been some clarification here that when I'm looking at this region here, since I'm doing chords, there's technically like no lines falling out here. So there's only 1 region on the outside. So whenever I interpret this, I'm going to basically just cut it off by the circle, treating them as chords. So there is no like extension out here. Looking at basically just like closed regions except for the outside part. but this still requires a little work for us to count the values in order to determine how many faces there are. We're only interested in the regions contained by the circle. So here I'm not writing n minus c plus f because my n is not the usual n here, right? Originally we just said n points, but this graph that I'm creating doesn't have n vertices. It's going to have n plus n choose 4 number of vertices. So now the harder part to still kind of figure out here is, well, this thing is going to look like a mess to count how many edges there are. I don't know if anyone has a suggestion, idea, like how would we determine, like counting the number of edges looks like a very complicated, well, maybe not too complicated, but it definitely doesn't look too simple to actually figure out. So by looking at this form of this graph, I would say at least the first step that will be a little easier for you to, I guess, interpret is if we have an understanding on the sum of the degrees, then of course I have that relationship with the edges, right? I can do half of that to get the number of edges. So therefore, instead of just directly doing this, we know the number of edges, right, is going to be equal to 1/2 times the sum of the degrees. So this still doesn't make it too simple here. But if we're looking at the sum of the degrees, at least part of this that should be easy for us is if I look at these n choose 4 vertices. Right. So if I look at any vertex, the vertices that correspond to intersections, it should be clear by how I define this form of the circle and the chords that, well, that this intersection vertex is going to have exactly 4 edges coming out. Right? The key thing is we assume that you can have multiple lines intersecting at this, 3 different lines intersecting at the same point. So therefore, each point that I see in there, or each vertex, when I correspond it to a graph, will have exactly 4 edges coming out. Oops, sorry, I forgot to put the 1/2. And then now the only remaining part we have to work with is now on the outer circle, right? Those vertices. So we do have to be slightly careful here because of how we're converting this original geometric figure into an actual graph exactly by the construction of how the circle looks. So for each vertex, as we said originally, so there's n vertices on the circle. And now I'm drawing a line between every 2 points that I see on the circle. So therefore, for each vertex, it joins to n minus 1 of them. So I have n minus 1 edges coming out. But you have to be careful how we drew this, like in terms of a multigraph, technically, is that originally in the circle itself, right, the 2 points adjacent, if you look at it in, like, I guess a clock form, right, for any point or vertex I see on this circle, it's already, in a sense, adjacent to the vertex, the 2 vertices that's either consecutive or successive to it. So therefore, each vertex that I see when I convert this to a graph is actually a multigraph, where this vertex joins to all n minus 1 other points on the circle, and I have these 2 that are coming out originally from the circle. So therefore, I need to add 2 more.
Could you restate the what we're trying to prove again real quick?
I'm applying Euler's formula to determine the number of regions.
So we want to show that what's the point of being a planar graph? That's where I kind of got lost.
Because wait, I don't. What do you mean by what's the
points on the circle as a planar graph?
Because I'm trying to determine how many regions divide the circle. That's the equivalent to how many regions, how many faces there are in that graph.
But doesn't there have to be intersection, and then it's not planar?
But that's why I'm defining. That's what part A is about. When they intersect, I'm defining this as a vertex.
Oh.
Does that make sense?
Yes. Yeah. Because then you'd have no crossing edges because you put a vertex.
Exactly. Yeah. Oops. This is 36. Are there any questions on that? So if you don't remember, since this was probably like 13 weeks ago, S of n comma n minus 2 is the Stirling number of partitioning the set 1 through n, bracket n, into exactly n minus 2 parts. So remember that this is looking at partitioning a set. And so you're just breaking this up into subsets. And here specifically, instead of S and K, we're looking at when it's exactly n minus 2. So obviously you're doing this at a number pretty close to either 1 or n to make it kind of reasonable that there aren't too many parts, that there still exists an explicit way to count the ways to do this. Maybe this is a little deceiving. Maybe I shouldn't write these numbers, because the key thing is when you partition, I'm not distinguishing each set. So we'll just picture, I guess, as this. Or sometimes it maybe even helps just like if n is 10, then we want to like k equal 8. So you basically have to do kind of a small case analysis on what can happen here. So again, the very important thing to remember is that when you're talking about partitioning bracket n, the set 1 through n, is that you're not distinguishing and saying, oh, if I partition it into 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10 as 2 parts, that's not a different case than 6, 7, 8, 9, 10, comma, and then 1, 2, 3, 4, 5. Right? A set doesn't have an ordering. So when I do a partition, there is no ordering on how I do this. And that's why I think it would have been more confusing if I would have labeled each of the boxes, because I'm not distinguishing what I'm placing in there. As if I put 1 in here versus, and then a 2, that's the same as 2 and then a 1. Right. So if we just look at the specific case of just n is 10 and k is equal to 8, kind of I would say the easiest way to think about this first is you could definitely have where every single thing has 1 element in it, and then 1 part has all the remaining. In this case, it would just be 3 elements. So your partition would look something like this: 1 element, 1 element, and then 1 part has like 3 elements. So therefore, one possible case is that this partition has all singletons except for 1 part that has size 3. Well, then from that part of size 3 that you're looking at, that's the partition, the block that has size 3, you better clarify, well, what elements are in there? But again, when I look at one of those pieces, those blocks, right, I'm not distinguishing these. This is a set, right? So ABC, there's no ordering. So therefore, out of the elements of n, I'm just picking 3. And remember, that determines everything else. They're singletons, there's no ordering. I'm not distinguishing and saying, okay, you pick ABC. I don't care if this is D and then E and then, or E and then D. It doesn't matter on the ordering because this is a set. All right, so now then, if it's not that specific case, you don't have too much more forms of what could happen. So again, if it helps you, you could just look at this numerically as in case. So it should be clear immediately that you obviously can't have this part, some part of size 4. So now you basically are saying, okay, now I could have some parts of size 2 or something like that. So if it helps you, again, you can imagine looking at like this. So I could have a part of size 2, another block of size 2, and then all the rest are singletons. I'm kind of out of space, so I'll just continue here. So again, you can just choose your two elements that you want here. But after you decided on those two elements, now you have to create another subset of size 2. But these are the subtleties you have to be careful on, right? Because when you're choosing the sets in this form, then you're telling me there is an order, right? The n choose 2, I could have picked AB, then I could have picked CD. But then choose 2, I could have picked CD first as two arbitrary elements, and then I could have picked AB. But I should be distinguishing this because this entire partition, there's no ordering on the sets. And so I need to divide out by 2. And then you can double check yourself that these are the only two cases that are possible, and understand that everything is decided from here afterward. But you can't have, 3 parts of size 2. There won't be enough, I guess, elements for you to break it up into 8 parts if you do it, I guess, in this example. And then it should be pretty clear that after this case, if you see that with one block of size 3, there clearly can't be a block of size 4, and then still break it up into like 8 parts. Are there any questions on that? So what I'm saying here is that you assign a seat, you just sit down at random, everyone's in the wrong seat, and then now what you're doing is, okay, you look at the person, I guess, to your left, and then you're like, all right, scoot over, everyone just like shifts over one seat. And then you keep doing that. And we're just saying that if you keep telling the person to your left, you're going to keep moving over, at some point, you should be able to see that at least 2 people must be in the same seat. So it should be pretty, I guess, reasonable that the technique you're going to apply here is pigeonhole. that you want at least two. So just you have to make sure your argument's clear on like how you argue this. I mean, it may seem pretty obvious to you, or you may say, well, I can do some like, I don't know, worst case scenario or something like that. But you should make your argument very, very clear to be exactly what is happening. So if you kind of look at, I guess, pictorially, you know, what is happening here, it should make sense that if you're wherever you're seated, right, you're already told you're at the wrong seat. So what you can actually do, right, is imagine that every single person is actually just given a piece of paper that states what seat that they should be at, right? That's their assigned seat. And then obviously everyone has a different one to seat them on 100 seats, but each person that looks at their piece of paper, right, is currently on the wrong seat. So it may be even easiest to imagine like whoever is currently sitting here in the wrong seat. Well, if this person is in the wrong seat, whatever number that is on his paper, well, there's only 99 other possible seats, right? So he could write down on his piece of paper how many shifts to the left does he have to do until he gets to his assigned seat. But he's already taken up one of the seats, which is wrong. So it should be clear that there's only 99 other choices where he can rotate to get to the correct seat. So if each person writes down their number of how many rotations they need, they can only write down 1 through 99 to get to their correct seat. But there's 100 people, right? So therefore, 2 people must have written the same number, which is the number of rotations they have to go to reach their correct seat. And so if everyone writes down exactly what this number is, how many times they need to rotate, well, there's 100 people, but only 99 numbers, so 2 people must have written the same number down. So it's a pretty simple argument if you kind of see, you know, the I guess trick to it. Otherwise, like I've asked this problem before, and then some people write, I don't know, like 2 pages about it because they try and, you know, give some like brute force argument or explain like in worst case scenario or something like that. But in reality, like this argument only takes a few lines. You just have to cleverly see like how you define the pigeonholes and the pigeons, and it's just that the holes here are just how many rotations you need, but there's 100 people, but only 99 possible rotations to get to the right seat. And so 2 people will have the same. Any questions on that? The interesting thing on doing some of these Ramsey theory questions is that it kind of relates multiple areas together. So obviously it relates to this graphs, relates to the concept of colorings, but also is going to use some kind of slick combinatorial way of arguing what's going to happen. So here we're not going to do like the diagonal value where the two numbers are equal. So R34 specifies that I'm looking at a red. I'll just do red K3 and then a blue K4. So here we're just going to kind of keep it simple. I'm not going to make it equal. So remember, if you're trying to prove that it's less than or equal to 9, what you're being asked to do is show that if you have a K9, no matter how you try and color this thing, it always assures that you have one of those two structures, right? That provides an upper bound that any possible coloring I do assures that I will have either of these structures. And here I'm coloring the edges, not the vertices. So the kind of hint is already, I'm telling you something about, well, you're going to use 9 vertices. The argument is similar to this through 3 case. It's just there's a little case analysis, and you have to be, I guess, a little careful how you're setting it up. So now just be aware that your argument has to be kind of clear, like which one is which, because you looking at the red or the blue is a different click size, right? So you can't just kind of do without loss of generality, because it depends on which one you're actually trying to form or force. So let's just look at the case right now that we have these 4 red edges, and this should be pretty simple to see what's going to happen here. So remember, this is complete, right? So I do have to join everything together here. But if I look at those, the graph induced on those 4 vertices, right, we should observe that for any of the vertices here, if there's any adjacency that forms that is going to be red here, then I formed a monochromatic or a red K3. On the other hand, right, otherwise, then if none of them are red, that would form a blue K4. So therefore, when I see that if there's just a vertex, which is incident to 4 red edges, the coloring on the induced graph of its neighbors is always going to force a red triangle or a blue K4. And then it should be reasonable, right? It doesn't have to be exactly 4 edges. If there's 5 red edges incident to this vertex, I can do the exact same argument. I can just even ignore the other edges. Right? So this takes care of the case that this tells me once I have, if I see any vertex with at least 4 red edges incident to the vertex, I'm done. It forces either a red K3 or a blue K4. So remember that I'm coloring the this is always looking at the complete graph, right? Yeah, so I didn't draw the edges, but remember that in the actual graph, it's complete. So everything, there must be an edge amongst all these vertices. Right, so I didn't put the edges, but just be aware that I'm coloring the complete graph. So there are edges between any of these two vertices on these four neighbors here. So if any of these vertices, whenever I look at an edge, if it's red, it forms a K3. So that means everything has to be blue inside here on the induced graph on these four vertices, which is exactly a K4. Because I'm looking at coloring the complete graph always. So let's see. Maybe I should have did this case last, but so the logic or the way I wrote this might be slightly confusing. So it's clear now that regardless, every single vertex I'm looking at cannot have more than 3 edges incident to it. So I'm going to be more specific because the last case I'm going to look at, I kind of just have to say it, otherwise this case 2 won't really make too much sense, is that I'm just going to find a vertex then that has 2 or fewer edges incident to it that are red. So I'm looking at this case where let's assume that every single vertex does have exactly 3 edges incident, red edges incident to each vertex. So you want to see what the kind of issue with defining it like this would be. So technically what I can do is if you're telling me every single vertex is 3 red edges incident to it, then what I could do with that original complete graph is let me just get rid of all the other edges that are blue. Which is then you're telling me if I look at the graph induced by the red edges, you have a 3 regular graph on 9 vertices, which is impossible, right? You would have an odd number of vertices of odd degree. Does anyone see what I can do here? It's pretty slick. It's a very simple argument, but you have to kind of see kind of what the structure looks like to help you. So this is the case where a vertex has at most 2 red edges incident to it. So that means the remaining that I'm looking at, which is 6 or more, must be all blue. So now, if these are all blue, I can now look at the induced graph on these 6. But what do we know? If we have 6 vertices, so meaning I can look at that as the complete graph, okay, 6. If I color that portion red or blue at random, well, what do I already know? So I know the portion induced on here always assures a monochromatic K3. Well, if there's a monochromatic K3 that's all red, then I'm done. I forced a K3 that's red. Otherwise, this forces a monochromatic blue K3. But then what happens here? This K3, along with all the edges that are joining to this one, form a blue K4. And therefore it forces it either way, that either I'll get a monochromatic red K3 or a monochromatic blue K4. And so therefore that proves that R34 is at most 9. So the value is actually 9. Obviously, I'm not going to go through a coloring to show you that on a K8 it doesn't have one. But it's sort of interesting, how you have to. This last case uses the argument of R33 that we did in class in order to prove this. And once you have that information, right, this argument is very short. Just observing there's a either red or blue triangle in here, which takes care of the 2 cases immediately. Any questions on that?
Yeah, so for case 2, we said the induced subgraph was invalid, and I agree with that. But is it a fact that, like, if we have a graph and some induced subgraph of it is invalid, does that make the whole graph invalid?
I mean, I think it depends on the conditions of what you mean. Like, I think your statement is very vague to like make that conclusion. Like obviously in the case where you would force a odd regular graph that has an odd number of vertices will be impossible, but I think your statement is a little too vague to like answer that exactly. I would agree for like the degrees of just as odd, it's going to cause a problem, but I don't think by how vague your question is, it definitely would not be a true statement because it depends on this, I guess, the conditions of the problem.
Right. Okay.
Yeah.
So,
Yeah, go ahead.
So in case two, we're just saying the induced subgraph is invalid.
Yeah, for the specific, yeah.
Okay.
So it should at least sort of make sense here if you're looking at this degree sequence per tree. As we proved earlier, right, there must be at least two leaves in the graph. And then the sum of the degrees is 2 times the number of edges, which is 2n minus 2. And so now the question is asking, okay, for these degree sequences that you're seeing, right, how many different sequences will work? So I'm almost out of time here anyway. Well, one thing you already know is by this, one of the conditions, right, is that the last two numbers have to be 1. But in addition to that, right, understand that you have this kind of restriction, right, where the numbers are non-increasing. And you want this non-increasing sequence of numbers to always sum up to this value, which in this case, right, I have the remaining part here that is going to sum up to n minus 4. And these two must be fixed, as we said, they're leaves. So understand that we're looking for a sum of numbers to be equal to 2n minus 4, subject to the condition that it's a non-increasing sequence of positive integers. So therefore, all this question is looking at, right, is partitioning the integer n, sorry, I guess 2n minus 4, into exactly n minus 2 parts. All right. Are there any questions, last words, anything you want to ask? All right, so it's been a pleasure. Just the exam will be in a week, the final exam. Just email me if you want to meet up or anything before the exam. Feel free to send an email. We can definitely find a time to meet up if you have any questions.